Hi everybody, and welcome to a new video in the video series on systems biology, digital twins, and AI. So we are still in block 2, and which means that we are using data to analyze the models. And we are still on identifiability analysis, which means that we are figuring out how well determined the parameters are that we estimate from data. And in the previous video, we looked at structural methods using these beautiful differential algebra approaches to calculate the results. And I told you about some of the limitations of that, despite the beautiful mathematics. And I advocated for instead using practical identifiability analysis. So in this video, we will look at those methods. So the question is p hat uniquely identified? Does it have a small uncertainty given the model and the concrete data set? So now we are not looking at the structure of the equations and we think independently of the specifics of the data sets. Now we are looking very concretely at the specific data set and a specific situation. What will we do? We will look at one option, which is the historically most widely used. It's still very widely used in certain applications, and that is to use local sensitivity-based methods, having to do with things like solving the sensitivity equations, the Fisher information matrix, and other related options. So I will go through the basics of those because they are very widely used and you should know about them. But I will also go through, in a similar way as for the structural analysis, I will go through some of the important limitations that you also should know about. And the key limitation is that it's actually not an identifiability analysis, but it's a prediction of the sensitivity, which is something else. Therefore, I would advocate for not using this, at least not to when you're really interested in the result. So instead, I will advocate what I think is the state-of-the-art approach, which is called profile likelihood analysis. But there are also some other good alternatives, which either come from the Bayesian community. You can use MCMC, Markov chain Monte Carlo approaches, or other methods like bootstrapping, which are also decent. And I will just mention that in the end of the video, but I will go through it in the next video, where we'll look at observability analysis, which is a related problem. Okay, so first, let's do the local sensitivity-based methods. So they are based on a very similar matrix as in the previous video. So you take the output y and you derive it with respect to the parameters. You can also do it with respect to the states, but here let's just do it with respect to the parameters. So here we have all of the derivatives for all of the y's with respect to the parameters. So this is called the sensitivity matrix, which is very similar to the observability matrix before. And these are the derivatives. It should be the total derivatives. And as I mentioned, when we talked about local optimization, there is a way to get these type of derivatives. Because you need them also when you do the local optimization. You need the same type of derivatives. How does y and x depend on the parameters? When you're optimizing parameter space, you need the derivative of the output with respect to the parameters, because this allows you to find the gradient that is used for the local optimization algorithms. And for that, we can use these sensitivity equations. So I mentioned most of this already. So basically what we want is these sensitivities, how the y, dy, dp, and those ones you can get if you have the xdp. So this is the chain rule again. So the hdx and the xdp. So the dependencies of H, which is the output equation, with respect to the parameters are either via the states, which do depend on the parameters, or explicit dependencies of the output equation itself. So this is typically where you have all of the Vmaxes and the Kms and so on, and this is where you have the scaling parameters. So we need the XDP to get the YDP. And this is where this idea again comes in of expanding the original set of differential equations to also have states that are all of the XDPs. So all of these guys that we need, the XDPs, we will be able to simulate those. So here we have the dt of the XDP, and we see that this depends on itself just as in a normal differential equation. So we can simply create a very, very long list of differential equations that describes the how the derivatives, all of the XDPs change with time. And you don't have to worry about understanding the details of all of these equations and how to implement them, so to say, or how to do all of these derivations. That is done automatically by software. So you can simply do some minor modifications to the way that you do the simulations, and all of this will be solved automatically. So that means that we can get all of this dydp. And the idea here is that by having these ones, there are some quite straightforward analytical formulas how to get the uncertainties of the parameters. So this is centered around something called the Fisher information matrix, which is basically dydp times dydp, and it's scaled by the measurement uncertainty here. And this is very related to this approximation of the Hessian that we have, that I talked about when we looked at these quasi-Newton optimization algorithms, where we need the Hessian, it's the second derivatives, and we did an approximation where we just used the first derivatives and we multiplied those together. This is basically what we do here as well. And I talked in the video on global optimization about that. Sometimes you look at the covariance matrices and the covariance of the parameters. So basically how they depend on each other and how well determined they are. That's basically given by the inverse of the Fisher information matrix. So you just have this thing here and you take the inverse of that. And it becomes this simple if the calculation of the covariance matrix, how the parameters depend on each other and on itself, so how well determined they are, it becomes this simple formula if the noise is always the same, which for all time points, which it often is. So you can go from this formula here to another formula here where the estimated parameter that we got out from the optimization is within the confidence region. So here we have the lower boundary and this is the upper boundary. So we just need to calculate this value here. And this is just the optimal value that we got. This is just a statistical distribution called the inverse student t-distribution. This is the measurement uncertainty. And this D here, this is the diagonal element for this covariance matrix, or the inverse of the Fisher information matrix. So you see that simply by looking at the diagonal elements here, we can just embed it in this scaling. We take the square root and we multiply it by these two guys, and then we get the confidence region. So all of this is very appealing, of course. It's just a simple formula. So you just do all of these things and you get them for free when you do the optimization anyway. But the problem is that there are some very crucial assumptions that you do when you get all of these formulas. And the key thing is that you assume that the cost function landscape looks like an ellipse like this. So here you have the optimum, and this is the sort of most uncertain direction. This is the most well-determined direction. And in practice, it might very well look in other ways. So it is fulfilled if you have lots and lots of data, if you have enough data so that you sort of have an identifiable system, then this is fulfilled. And there are general results, for instance, in the book by Lennart Jung on system identification, a very famous book. This is already fulfilled, so to say. But in systems biology, what you want to know is if the parameters are identifiable. And if they are not, then you have these dependencies between the parameters, which means that it will not be a well-determined ellipse, but it might be sort of non-linear dependencies like banana shapes, where the parameters along this entire banana shape in the parameter landscape, they will all give the same output. And if you take a sort of local part of this banana and you just do the sensitivity-based calculations, and when you consider it to be an ellipse, it might look like it's identifiable, but it's just because there is a non-linear dependencies in the parameter landscape. So basically here we need to assume that the system is identifiable for us to know that we can apply this approach, and the approach is used to determine if it is identifiable or not. So it's really putting things backwards, and that's why I strongly advocate against using this approach, because it's really not meant to be an identifiability analysis to know if the parameters are identifiable if we don't know it, so to say. But it's more a prediction of how the output depends on the parameters, which is the sensitivity, and that is a prediction, and that prediction needs an uncertainty, and this is the way that you should treat this. So this is straightforward, but I would really advocate against it. So what should you do then? Well, it's a very simple method. It's a slightly more computationally demanding, but it's very straightforward and very intuitive. So you pick one parameter that you want to know the uncertainty of, and then you start at the optimum, and then you step away from the optimum. And for each value that you have when you step away from the optimum, which is here denoted Pij, so you step away for the jth time, you optimize all of the other parameters. So you see how good can you agree with the data, how low can the cost function be when this parameter is this value, which is deviated from the optimum. So you get this sort of trade-off of moving away from the optimum for one parameter and seeing how well can the other parameters compensate. So you have this new optimization problem where you optimize over all the parameters with the additional constraint that this Pi parameter, this is equal to some other value. Otherwise, you do an optimization to the data, just as normal. And if you have that it's identifiable, then at some point you will not be able to compensate. The other parameters cannot be optimized to maintain the good agreement with the data. So at some point, the cost will simply be too high. The agreement will be too poor. And then you have basically the upper, at that cutoff, you have the upper value for how big that parameter can be, or how small if you're stepping downwards. So basically you have some optimum here. This is this modified cost function where you fix the value of one parameter. And here you have that parameter that you want to have the uncertainty for. This is the optimum. And here you have one option for a cutoff. And if you look at the curve and it looks like this, then you should sort of realize that maybe we should actually increase the cutoff to some other value. That is sort of not dependent on these sort of bends here. So this is because here you also have acceptable values over here. So this should sort of be the cutoff. And there are various ways to choose this cutoff. But basically, this is the idea. As you are stepping away here, you're optimizing over all the other parameters. And if it is identifiable, the further away you step, the worse the other parameters are at compensating for that. And if it's not identifiable, this will be completely flat. So then the other parameters can compensate completely for this parameter. Okay, so we realize that this cutoff, we need to choose it because the actual confidence interval will depend on the value. So you can either use some statistical tests, and we'll talk about some of those statistical tests, which just has to do with the agreement with the data, like a chi-square test, for instance. But you can also base them, and this is the traditional way to do it for the profile likelihood, is that you base it on the cost value at the optimum, and then you take that cost value plus the inverse of a chi-square distribution with 1 degree of freedom. If you want to have the sort of the smallest confidence interval possible, where you only require that each individual parameter should lie within the confidence region 95% of the time, if here you have 95. But if you want that all parameters lie simultaneously within all of the confidence intervals for the entire block of parameters, so to say, then you should have the degrees of freedom in this chi-square distribution should be the number of parameters. And there are various ways to compensate for this to have a value in between. So it's a little bit of a feeling and a heuristic for exactly how to use the cutoff. So the important thing is actually to look at this shape. Does it look like a U like this, or does it look flat? And is it very noisy and shaky and goes up and down across the cutoff, or is it like a very nice curve? So if it's a very nice curve and it looks like a U, then it is determined. And then if it's not, if it's a flat line, or if it sort of very goes up and down, then it's not well determined. Okay, so just finally in the end, there are 2 other approaches. One is called bootstrapping, and one is called Monte Carlo or Markov chain Monte Carlo approaches. And those are also viable alternatives. I will go through them in the next video when we talk about not the identifiability analysis, which is to determine the parameters uniquely, but observability analysis, which has to do with determining other model properties. So that was basically it for this video. Thank you for listening.